Heat transfer 4. If the glass surface temperature were to be lower than the dew point, is the water vapor in the air that leaves to the lower surface temp glass the condensation, since heat transfers from high to low temperature and the dew point is the 100% saturated state, any transfer of heat to a lower temp surface would cause condensation. So let me make sure I'm reading the question right. Is the water vapor in the air that leaves to the lower surface temp glass the condensation? Yes. Yes. Okay. I had to think about that for a second. It is the water vapor that's in the air that, when you say leaves, it changes state. So let's think of a super simple example. Let's just imagine you're drinking a glass of ice water on a hot, humid day, and condensation forms on the outside of that glass. When I was a kid, I was kind of naive. I didn't really know what was going on. I just knew that sometimes when I pick up my glass of ice water, it slips out of my hands and, spills over or something like that. But I always thought, I didn't put it together. I didn't think about psychrometrics as a kid. I just thought somehow the water, the cold water, is getting through this glass. It's ridiculous now thinking about it, but at the time, that was what my sort of innocent brain thought. But in fact, that's not at all the case. It is the water vapor that's very much in the surrounding air, that's in the space, that's in the room that the glass sits in, which contains water vapor. Because what is air? Air is a mixture of nitrogen, oxygen, a few other trace elements, but mostly nitrogen and oxygen. We call that dry air. And then also water vapor. We call that moist air. And air is rarely, if ever, perfectly dry air. It's almost always moist. The question is a matter of degree. How moist is the air? Maybe it's 50% humidity in the room you're sitting in. Maybe it's a hot, humid day and it's 80% humidity. In any case, the water that forms on the outside of that glass, that condensation, is a result of the air being cooled past its dew point. So the definition of the dew point then is the minimum temperature that some parcel of air, it's not all the air in the room, it's the air that's coming in, the air might be moving a bit, but some of that air is coming into contact with that cold surface. And as a result, condensation forms. Water vapor from that air changes state. And that happens whenever we cool air past its dew point. So just as a reminder, what's happening psychrometrically, we can draw that on the psych chart. Sometimes when we deal with air conditioning processes, we're in a rush to draw slanted lines. For instance, if you start with some room condition, call that state 1, and we know that we're doing sensible and latent cooling, we're very eager to draw some line that's down and to the right to state 2. But it's a good idea from time to time to remind ourselves what's really happening in an air conditioning process. We don't actually have the luxury of moving on a slanted line, although that's convenient for analyzing things and we do it often. But let's be reminded what's really happening. Some parcel of air is being cooled, and you can't force water vapor out of the air by any other, well, that's not true. You can use a desiccant, which directly absorbs water vapor from the air, and then that's a way of doing purely latent cooling where you're able to go vertically straight down. But when you're using an air conditioning system with a cold coil, let's say, you don't have the luxury of going straight down. So how do you wring moisture out of the air? Well, you have to cool sensibly. That's all you can do. And that's exactly what you do. So you move horizontally to the left to some point 2. And eventually, you can't go any farther. You run into the saturation curve. We say that is 100% saturated air. So its dry bulb temperature is much lower, but its dew point temperature is the same. So the dew point temperature is a function of the condition of that air. So whatever this air is, maybe it started out and it was 75 degrees Fahrenheit and 50% humidity, let's say. For that fully defined state, we can look up the dew point. We can use a psychrometric calculator to do that, or we can just use the psychrometric chart, find that point, and then move horizontally to the left until we hit the curve. And whatever temperature we hit the curve at, that is the dew point temperature. You can read that off from the horizontal axis, or you can read it directly off this curve. So the process of going from 1 to 2 is purely sensible cooling. If we cool it further, if we go onward from state 2 to some other point further down the line, we'll call
Couple
that
more.
state 3.
You got range.
Then what happens is we continue to cool sensibly. If we're going to the left, the dry bulb temperature at state 3 is going to be lower than the dry bulb temperature at state 2. But now we also strip moisture out of the air because you cannot continue. If we continue horizontally, we'd go off the chart. That's not possible. So we have no choice but to slide down the curve in order to stay on the chart. So this is 100% air at T2 dry bulb, but as we slide down, we end up with 100% saturated air at T3. And now we have a lower dew point as well, because the dew point temperature is T2 for state 2 and it's T3 for state 3. And that's why it's useful to use the vertical axis as well, where we're able to define the humidity ratio at 1, which is the same as the humidity ratio at 2, because we've only done sensible cooling. And the process from 1 to 2, if we were to kind of summarize this, is sensible cooling only. Sensible cooling. And the process from 2 to 3 is sensible and latent cooling. And we would say, of course, that the humidity ratio at 3, draw this line over. Sorry for the not so horizontal lines. The humidity ratio at 3 is less than at 1 or 2. And the relative humidity at 2 is the same as the relative humidity at 3, which is 100% saturated. So that's a long explanation of dew point, but in summary, dew point is the minimum temperature that some parcel of air can be cooled to before condensation begins.